Welcome all to the next session of Fundamentals of Food Process Engineering. So in this session we'll be discussing the syllabus related to week 10, and we'll also look at the problem that was posted in the discussion forum at the end of the lecture. So question 1, ribbon blenders are used for A. Liquid, B. Dough and paste, C. Powder, D. All of the above. So what are ribbon blenders? Ribbon blenders are used for mixing two products, and these are generally powders. So what happens in a ribbon blender is that if you can look at the picture, this is a trough. The casing or the horizontal tray kind of stuff is called tray kind of an equipment is called as a trough. So inside this trough, you can see a shaft with a ribbon-like blade attached to the shaft. So this is why it is called as a ribbon blender. So what happens in a ribbon blender is that you send in the powder through an inlet, and the shaft stirs, causing the mixing of two powders. So what happens is, if you actually look at a zoomed in picture of a ribbon blender blade, you'll actually have an inner helical blender and outer helical blender. So both these blades will rotate in opposite directions and in different speeds. So because of this opposite direction and different speed, it will ensure better mixing of the powders, and hence we use powders in ribbon blenders, that is dry solid powders in ribbon blenders. So the answer to this question is option C. So dough and paste actually have they're semi-solids, or they're not completely solid in nature. They kind of coalesce with each other, and hence a different kind of a blender is used for dough and paste as well as liquid. Ribbon blenders are only used for solid powder-like substances. So ribbon blenders can be used in both batch as well as continuous mode, where you'll have an outlet as well, or else you will just send the powder in, you will mix it properly, and then after the batch time is over, you will take out the mixed powder. So the answer to this question is option C. Moving on to question 2, which of the following velocity component acts in a vertical direction in a liquid mixer? A. Radial velocity component, B. Axial velocity component, C. Tangential velocity component, and D. A combination of radial as well as a tangential component. So when you are dealing with liquids, you need to use an agitator or an impeller to induce a specific flow pattern inside the mixer. So you will have different kinds of impellers and different kinds of agitators that will induce a certain kind of a flow pattern, and these flow patterns can be of three types. That is, one is radial, one is axial, and the other one is tangential. So these differ in the direction of the velocity component. So if you look at the picture here, A is for a radial velocity component. So here you can see that whatever the impeller or the agitator induces a velocity component where your liquid will flow from the center to the wall of the container, and then from the container wall to back to the center of the shaft. So here you can see whatever the velocity component is, it is in the radial direction. That is, it is perpendicular to the shaft, perpendicular to the mixer shaft. That is, if this is the mixer shaft, you can see that the velocity component is perpendicular to the mixer shaft. So this is what happens in a radial velocity component. That is, your liquid will flow from the center to the end of the walls, and from the walls back to the center. This is what happens in a radial velocity component, radial flow pattern. In an axial flow pattern, this is axial, I'm sorry, this is radial and this is axial. So radial, you'll see it goes from the center to the end of the walls, and from the walls to the center back again. So this is axial. So since it's very similar for both, from you look at the top view, both of these are pretty similar, but if you look at the side view, here you can see the flow of the liquid is from down to top and then back to down. But here you can see it's both from down to up. That is, your liquid will flow to the walls and back to the center. Again, the liquid will flow to the walls and back to the center. So B is radial, A is axial. So A, you can see it is flowing parallel to the shaft, parallel to the mixer shaft. The liquid is flowing downwards, parallel to the shaft, and then it goes upwards and back again downwards. So here you can see a vertical direction of the liquid flowing, and it is parallel to the shaft. This is known as an axial flow pattern. In case of a tangential flow pattern, you can see that the liquid is rotating in a same horizontal plane. This is tangential, that is your velocity component is tangential to the liquid flow. Your liquid will always flow in a circular manner like a whirlpool, and your velocity will be the tangent to that whirlpool or a circular motion. So this is what happens in a tangential flow pattern. So as you can see from the diagram itself, that is the side view of the diagram, you can see that only in an axial flow, the liquid flows parallel to the shaft and it goes in a vertical direction. That is what happens is the liquid will reach the bottom of the tank and then rise upwards back into the suction of the impellers. So there are different kinds of impellers that are used to generate each kind of a flow. So for axial flow, a propeller is kind of an agitator that will help in the axial direction of the axial mixing of the fluid. So propellers are used for an axial flow of the liquids, and one positive or one advantage of an axial flow mixing is that if you have a lot of solids that is deposited at the bottom of the tank, this kind of an axial mix will take the solids from the bottom of the tank and bring it to the surface and then mix it properly. So this might not happen in a tangential flow, but this kind of a solid deposition at the bottom will be mixed thoroughly because of an axial flow maintained in the system. So A is again axial, B is radial, and C is tangential. The answer to this question is option B. The axial is the one that induces a vertical direction velocity component. Question 3 is the same part of the previous question. Which of the following velocity component tries to move a liquid in a circular motion on a horizontal plane? So if you look back in the same diagram, you can see that this velocity component that tries to move the liquid in a circular motion in a horizontal plane is the tangential flow velocity. So what happens in a tangential flow velocity, pattern is that your liquid will start moving as in a whirlpool kind of a manner. So your liquid is moving in a circular motion in the same horizontal plane, and the velocity component that you will be considering is when at a whirlpool at a particular point your velocity will be tangential to the circular motion of the liquid. So the answer to this question is option C. That is, in a tangential flow, the liquid moves in a circular motion in the same horizontal plane, and the velocity component is tangential to the circular flow of the liquid. And what happens when you stir it at a very high speed is that it will form a much bigger whirlpool. So you'll basically have only air here, and all your liquid will be thrown out to the walls of your stirrer. That is your mixing equipment. So basically, your liquid will experience a centrifugal force where you'll have only air in the middle of the shaft, and your liquid will be thrown out to the walls of your equipment. So what happens in this case is that when you have solid particles in your fluid that you are mixing, when it's thrown towards the walls of your mixing equipment, it will settle down at the bottom of the tank. So tangential flow will not be able to take these settled down particles and mix it properly when you have a very high vortex formation. So in order to prevent these vortex formation, so as you can see, when you have a vortex, you will not have proper mixing because you will have something called dead zones here. You will only have a whirlpool and it will be a very minute mixing only in this region. Whereas these corners of the equipment will still remain unmixed or segregated. So your mixing efficiency is very poor when you have a very high vortex formation. So in order to improve the mixing efficiency, we introduce something known as baffles as seen here. So as you can see, these baffles will break that whirlpool and hence prevent a strong vortex formation. So you won't have a circular motion like that. These liquid will hit the baffles and it will break the circular motion and hence prevent vortex formation and improve the mixing efficiency in your mixing equipment. So the answer to this question is option C. It's the tangential velocity that causes a circular motion of the liquid. Moving on to question 4. Power number is the ratio of A. Inertial force to viscous force, B. Inertial force to gravitational force, C. External force to inertial force, and D. Reynolds number to Froude's number. So we'll look at what each and every of these force mean. So the ratio of the inertial force to the viscous force is actually your Reynolds number. So Reynolds number is a dimensionless number which is defined by the ratio of inertial force to viscous force. That is not the same as the power number. So A, inertial force to viscous force is actually Reynolds number. B, inertial force to gravitational force is your Froude's number. Yeah, so C, external force to inertial force is what is your power number. So all these numbers, power number, Reynolds number and Froude's number are dimensionless variables that is used to define mixing in a particular system. So you can use Reynolds number, Froude's number and power number to detect how efficient or how efficient the mixing process is and how much power is required to maintain that sort of a mixing. So you'll need all these three numbers to determine the mixing process, the power requirement and so on. So that we'll discuss at the end of this lecture. So inertial force to viscous force is Reynolds number. Inertial force to gravitational force is Froude's number, and your external force to the inertial force is your power number. So the power consumption in a mixed system, in a system that is being mixed, for that certain power is required to mix the system, that is to rotate the impeller and all, and to overcome the resistance by the fluid. All those require power from your side. So power consumption in a mixed system can be related to the operating variables. That operating variables include the viscosity of the fluid, the density of the fluid, and the speed at which you're rotating. So all these are known as operating variables. So your power that you require to mix a fluid will depend upon the kind of the fluid that you're dealing with, the kind of the agitator that you have, whether you have multiple blades, you have a single blade, you have multiple sets of pairs of impellers. So all these will also determine the power consumption in a mixed system. So the relation between your power consumption and your operating variables is given by the power number. Power number is the ratio of external force to the inertial force. So, but you can it's not the ratio of Reynolds number to Froude's number, but it is dependent on the Reynolds number and Froude's number. That is, you can say that power number is a function of Reynolds number and Froude's number. Reynolds number is A, inertial force to viscous force. Froude's number is inertial force to gravitational force. So if you do a dimensionless dimension analysis, you will find that your power number NP is equal to P, which is your power consumption of the system, divided by rho, which is the density of your liquid, Ni, which is your impeller speed, the speed at which you are rotating the impeller, which is in revolutions per second. So Ni cube Di raised to 5. So Di is the diameter of the impeller. So you can see here that your power number is related, or your power consumption is related to the density of the fluid, your speed at which you are rotating the impeller, and Di, which is the diameter of the impeller that you are using. So your power is related to your operating variables through your power number. So the answer to this question is option C. So so if you guys have any doubts, you can just post it in the discussion forum, since not a lot of you are present in the class today. So you can post it in the discussion forum and we can discuss it later on as well. Moving on to question 5. Which of the following statement is true? A, mixing index increases with time. B, mixing index decreases with time. C, mixing index is constant for a particular fluid. D, mixing index reduces by half with time. So for this, we need to first understand what a mixing index is. Mixing index will tell you how much of the mixture that you have is mixed and how much it is segregated. So if you have two components A and B and you put it inside a container, at say time t equal to 0, both of them will be segregated. That is, you won't have any mixing. But if you start rotating, or if you start put it in a mixer where the two components will start mixing, with time you will see that your segregated system will slowly start becoming a fully mixed system. So you can find out from mixing a parameter known as a mixing index, you can find out at that particular time how much of the components have been mixed, that is, to what degree it has been mixed. So mixing index actually changes with time. So at time t equal to 0, you will have two completely segregated components. At say time t equal to infinity, you will have a proper mixture of the two components. So your mixing index at each time point will vary. That will give you the degree of mixing that has happened at that particular time t. So mixing index is actually a dimensionless variable, and for a real mixture, the mixing index can be given as m is equal to s naught square minus s square divided by s naught square minus s infinity square. So in this case, S naught is the variance of segregated system. That is, you can say maybe at time t equal to 0, when you have segregated system, you will have the variance of that particular system. Like say we have a tank, you're putting both the components A and B inside it, and at time t equal to 0, you are taking out, let's say 10 samples, 10 small samples at time t equal to 0. So from those 10 samples, you will calculate the fractional component of that particular fractional component of the component that you are looking for. Let's say you have starch and some other inert material that is being mixed, and you want to look at how much starch is being mixed at time t equal to infinity, say. So at time t equal to 0, you'll take 10 samples from the mixture and you'll find out how much starch is present in each of those samples. From those samples, you will calculate the variance, and S naught will be the variance of the segregated system or at time t equal to 0. You will take a certain amount of samples and then you will find out what is the concentration, or rather the fractional volume of the component that you are dealing with, and from there you will calculate the variance, and that is S naught. So you need not worry about this. We'll do a more detailed numerical of this in the later few questions. So S naught is the variance of the segregated system, let's say at time t equal to 0. S is the variance of the real mixture at time t. Say the total mixing time will take somewhere around 100 seconds. You have taken 10 samples at time t equal to 0. That will give you S naught. And let's say at time after 20 seconds, you are again taking 10 samples. So that will be your S. That is S at time t equal to 20. You will take multiple samples. From there, you will calculate the fractional component of the desired product. That will give you S. S infinity is the variance of the fully mixed system. Let's say if it is taking 100 seconds, S infinity will be your variance at time t equal to 100 seconds. So S naught is of this completely segregated system. S infinity is the variance of a fully mixed system, and S is somewhere in between those. That is, at any time t, S will be the variance of that particular real mixture. So this is just basic statistics. Variance can be given as the root of xi minus x bar the whole square by n. Let's say you have n different samples, like at time t equal to 0, you are taking 10 samples. So in this case, n will be equal to 10. So xi will be the fractional component of, say, some component A at each of those samples. Let's say your first sample will contain 0.2 or 20% of your A component. So xi will be 0.2. And second sample, let's say you have 40% of the component. So xi will be 0.4. So xi will be the fractional component of the particular product that you are looking for. So that will be xi. X bar is your mean component. That is, when you have a fully mixed system, let's say you want a fully mixed system with a fractional component of 0.5. So x bar will be 0.5. That is your desired component or your mean component of all the samples that you have taken. So x bar will be the mean component, mean fractional component divided by n, which is the total number of samples you have taken at that particular time. So this will give you variance. So since you're dealing with S square, you will take a square on both the sides. So you will have sigma I equal to 1 to n xi minus x bar the whole square divided by n as your S. So if you want to look at mixing index, as time increases, the system gets more and more mixed. Hence the various S reduces over time. So if you look at the previous formula here, your xi will get more and more close to x bar. That is, you will get more and more close to your desired component, the desired fractional volume that you are looking for. So xi will get more and more close to x bar as time increases, because you are mixing it continuously. So your S will reduce over time. So if your S reduces over time, your S square will also reduce over time. So if S square reduces over time, your numerator will become numerator will become very large. That is, your S naught square will be constant. S infinity square will be constant for a particular component that you are dealing with. So given that rest of these are constants and s square is reducing over time, your numerator will increase and hence your m will also increase with time. So as time increases, the system gets more and more mixed, hence the various s reduces over time. That is, the difference between the fractional component and the mean fractional component reduces, and hence as s decreases, m increases with time. So if this is very confusing, we can also look at it from from your rate of mixing point of view. So a rate of mixing, that is dm by dt, is directly proportional to the amount of mixing that is left. So m will tell you how much it is mixed right now. 1 minus m will tell you how much more mixing is left. So dm by dt, that is the rate of mixing, is directly proportional to how much ever more mixing of the component that is left. That is 1 by 1 minus m. So if you remove the proportionality sign, you multiply it with a proportionality constant, which is k. So dm by dt is equal to k into 1 minus m. So now if you integrate both the sides, that is if you bring 1 minus m this side and dt this side, and you integrate it from 0 to m and from 0 to t, you will get ln of 1 minus m is equal to minus kt. And if you rearrange this, it is m is equal to, you will take an exponent on both the sides, 1 minus e power minus kt. So here you can see from this equation also you can find out what happens to your mixing index when time increases. So if you look at this equation, if time increases, this particular value goes down. That is e power minus kt reduces. And hence 1 minus e power minus kt will increase, which is your m. So hence m increases. So you will have your m varying between only 0 to 1. 0 will be a completely segregated system where both of them do not mix, and 1 will be a completely mixed system where both the components are completely mixed. So your m will always vary from 0 to 1, and as time increases, you will actually see that your m is reaching to a unity. That is, m is slowly increasing to 1 as time increases. So the answer to this question is option A. Moving on to question 6. Vortex formation can be prevented by A. Positioning the mixer shaft off the center. B. Use of baffles. C. Installing two sets of impellers rotating in an opposite direction. D. All of the above. So as we saw in one of the previous questions, you can see that when you would remember that when you do when you incorporate a tangential flow pattern inside your mixing equipment, you will see that a whirlpool kind of phenomenon is formed. So if your impeller speed is very very fast, this whirlpool will be very high or very drastic. So in that case, a vortex formation will happen. So this is what happens when you have a tangential velocity profile inside your mixing tank. You will have a vortex formation where here there is only air and all your liquid is thrown towards the walls. That is, your particles will experience a centrifugal force and will be thrown towards the walls, resulting in very poor mixing. Hence, vortex formation is not preferred much in your mixing tank. So in order to prevent vortex formation, there are multiple steps that can be taken. First is the use of baffles. So these perpendicular blade kind of equipments that you see here, parts that you see here, these are known as baffles. So what will happen is, instead of forming a whirlpool, these liquid component will now hit with the baffles, and this will disrupt the whirlpool, the vortex formation, and result in proper mixing. So yes, you can use baffles to prevent vortex formation. Apart from that, you can also position the mixer away from the center. So generally, all this while where we were seeing, your impeller is always present at the center of your tank. So instead of keeping it at the center of the tank, you will keep it towards the walls of the tank, so that now even if there is circular motion, again your liquid will hit the walls instead of the baffles right now. It will hit the walls, and hence your circular motion is disrupted. So you won't have a proper circular motion here. It will go towards the walls, hit, and then come back again. So your vortex formation is prevented even if you keep the mixer shaft off the center. Or you can do one more thing. You can place the shaft in the center itself, but at an angle. So instead of keeping it at 90 degrees to the base of the mixing tank, you can keep it at a slightly different angle. And because of this angle of the impeller to the base of your tank, again your vortex formation is reduced or prevented. So you can either position it off the center or you can place it at a certain angle. Apart from this, you can also install two sets of impellers rotating in an opposite direction. Let's say you have one set of blades here and you'll have another set of blades on top. So this will move, you'll have two sets, that is two shafts coming in, or you can have multiple blades rotating in a different direction. So the moment you have two impellers rotating in different directions, this will prevent a circular motion and you will have a very proper mixing happening and preventing of vortex formation. So in fact, all these three steps will prevent vortex formation and ensure proper mixing. So just to summarize, in a vortex, particles experience a centrifugal force and are thrown towards the walls. The large solid particles, as they hit the walls, settle down at the bottom, hence resulting in very poor mixing. So vortex is prevented by the use of baffles that disrupt the circular motion, or by positioning the mixer shaft off the center or placing the shaft at an angle can also help reduce the vortex formation. Additionally, vortex can also be prevented by using two sets of impellers rotating in an opposite direction that will also prevent disrupt the circular motion of the liquid. So the answer to this question is option D. All of these techniques can be used to prevent the vortex formation. Moving on to question 7, we will move on to numericals where we will properly understand how to calculate the mixing index from the variances that I was discussing before. So in mixing operation, 15 kgs of an active compound and 85 kgs of an inert material are mixed. The results in weight percent of active compound after mixing for 10 minutes were 21.8, 21.8, 23.0, 21.4, 22.3, 22, 22.7, 20.9, 22 and 21.7%. So you can see here there are 10 different samples taken at time t equal to 10 minutes, and in each of these samples you are measuring the amount of the fractional percent of your active compound, and these were the fractional percent of active compound present in each of those 10 samples. We need to calculate the mixing index after 10 minutes, and these are the four options given: 0.998, 0.9997, 0.9851 and 0.9805. So we look at how to calculate the mixing index at a certain time point t equal to 10 minutes. So as we discussed before, mixing index of a real mixture can be given as follows: m is equal to s naught square minus s square divided by s naught square minus s infinity square, where s naught square is the square of the variance of a segregated system at time t equal to 0. S infinity is the variance of a fully mixed system, that say at time t equal to infinity, and S is the variance of a real mixture at time t. So here t is 10 minutes, so we'll calculate the variance at time t equal to 10 minutes. So variance can be calculated, the square of variance, that is S square, can be calculated as sigma I equal to 1 to n xi minus x bar the whole square by n. So n is the number of samples that you have taken at a particular time. In this case it is 10, and xi is the fractional component at each of those samples. Here 21.8, 21.8, 23 are all xi. X bar will be your mean fractional component of all these samples taken considered together. So we look at a table where we will calculate this S square. It's pretty straightforward. It's the same as your statistics that you have. So I have the first column as 1 to 10, that is I have 10 samples taken, and your second column has all the fractional component of that your active ingredient that you're looking for, but instead of a percentage we are looking at your fractional component. So you're actually dividing it by 100. So whatever is given in the previous slide, these are all percentage, so you're looking at fractional component only. So you're dividing all of these by 100 to get your column 2. So 21.8 will be 0.218, 23% will be 0.23, 21.4% will be 0.214, and so on. So the x values are given in the question. So for figuring out your S square, we need to find out what is the mean fractional component required. So the mean fractional component is the mean of all these values. So if you take an average of all the 10 values, that is summation of all these x divided by 10, you will get your average as 0.2196. So this is your desired fractional component or your mean fractional component, that is x bar. So you need to find out what is the variance. So x minus x bar can be given as your 0.218 minus 0.2196, which is minus 0.0016. Same 0.23 minus 0.2196, which will give you 0.0104. So like this, you will calculate x minus x bar for each and every sample. So this will give you x minus x bar. But as you can see here, variance is the summation of the square of this difference. So you need to first square this and then do a summation of all these values, then divide it by n to get your s square. So we do a square of all these values. That is, the square of minus 0.0016 is 2.56 into 10 power minus 6. The square of 0.0104 is 0.001082, and so on. So you will do a square of all the values that are present in column 3 and you will place it in column 4. So the summation of this is your I equal to 1 to n x minus x bar the whole square. The summation of I equal to 1 to n. So if you add all these values, you get 0.003304. So this is your numerator of your s square. This will be your summation of x minus x bar the whole square. So your s square, that is your variance, is equal to your summation 0.003304 divided by n, which is your total number of samples that you have taken at a particular time. So in this case, you have taken 10 samples. So we are dividing 0.003304 divided by 10, which is equal to 3.304 into 10 power minus 5. So this is how you will calculate the variance at any particular time t. So if you have, let's say, a time t equal to 20 minutes, you are taking 5 samples. So then your n will be equal to 5. You will perform a same kind of calculation to find out your s square at 20 seconds. At 20 minutes. So for an unmixed solution, that is your S naught can be given, S naught square can be given as P into 1 minus P. So P is your fractional component of the active ingredient that you're looking for. So in this case, you're looking for an active ingredient and you have an inert material. So the active ingredient is what you're measuring at each of these samples. So P will be what you are trying to measure at time t equal to 0. So as you can see in the question, we have 15 kgs of active component with 85 kgs of inert material. Since you are measuring the active component only, this will be your P, this will be your Q. So P is equal to 15 kgs, that is 15 divided by 15 plus 85, which will be equal to 0.15. So P is always the fraction. So you have to divide your the total amount of active component that you have divided by the total amount of material that is present inside the mixing tank. So 15 divided by 15 plus 85 will be your P. Your Q will be 1 minus P. So S naught square is equal to P into 1 minus P, which is the fractional component of the material that you are looking for at time t equal to 0. So P is equal to 0.15, and if you substitute this in S naught square, you get 0.15 into 1 minus 0.15, which is equal to 0.1275. So this is your variance at time t equal to 0. Now for mixing index, we need to find out what is the variance at time t equal to infinity or a completely mixed solution. So for fully mixed solution, S infinity square is equal to P into 1 minus P divided by capital N. So you need to note here that small n and capital N are completely different. Small n is the number of samples you are taking at that time to measure the variance. Capital N is the total number of particles that are present inside the mixing unit. So if you have, let's say, 1000 particles that are being mixed, that is 500 particles of your active ingredient and 500 particles of your inert material, then 500 plus 500, capital N will be equal to 1000 particles. So N will be the total number of particles. Capital N is total number of particles, and small n is the total number of samples that you are taking to measure the variance. So those are completely different concepts that you need not confuse with. So S infinity square is equal to P into 1 minus P divided by N. So in this question, if you notice, we are not being told that how many particles we are mixing. So in this particular case, when you are not aware of how many particles you are mixing, you can safely assume that you have infinite number of particles. So you can actually assume n is equal to infinity. So if you assume n is equal to infinity, S infinity square will be equal to 0. So this is only if you don't have a specific number of particles mentioned. So if you look at the lecture videos, in one of the question, you will actually have n given in the question. Only then you will have a certain value of S infinity square. Otherwise, if you don't have capital N or the number of particles mentioned in the question, you can assume it to be infinite, and hence S infinity square will go to 0. So if you substitute all these values inside the mixing index formula, You have S naught square as 0.1275. S square we calculated from the table. S infinity square is 0. So M is equal to 0.1275 minus 3.304 into 10 power minus 5. This is what we calculated from the table from the 10 samples that were given in the question. So S square is 3.304 into 10 power minus 5. Your S naught square is again 0.1275 and S infinity square is 0. So if you now calculate, M is equal to 0.9997. So as you can see, since M is very close to 1, you can actually say at time t equal to 10 minutes, your system is actually very well mixed. So the answer to this question is option B. The more M is closer to 1, the more better your system is mixed. The more it is close to 0, the more improper there is mixing or more segregated the components are. So the answer to this question is option B. Moving on to the next question. Question 8. The initial proportion of vegetable powder to starch in a mixture is 40 to 60. The variance of the sample after 4 minutes of mixing is 0.09. How much time is required to reach a variance of 0.05? Assume a large sample size. So if you look here, we know what is the proportion in which both the components are mixed, vegetable powder to starch. So we know that we are looking for vegetable powder in this case. So your P will be equal to 40 divided by 40 plus 60, which is 0.4. So P will be equal to 0.4, Q will be equal to 0.6. And here you are looking at after 4 minutes of mixing. So time T is equal to 4 minutes. And in that case, your variance, that is your S square, is already given in the question. So instead, like last time, instead of calculating from the table, like say after taking 10 samples, here you are already given what is S square. So S square at time T equal to 4 minutes is 0.09. So we need to find out what is the time when your S square is 0.05. And here it is already given that we have to assume the large sample size. The moment you assume, it is given that you are going to assume a large sample size, you can take n is equal to capital N is equal to infinity. So we will proceed with the same steps as before. S naught square, which is your variance at time t equal to 0, is equal to P into 1 minus P. That is, P is the particle that you are looking at, which is generally your smaller amount of component that you are looking at. P is generally, let's say if you have 40, 60, P is generally the 40 that you are looking at and Q is 60 generally. So P is 0.4 and S naught square can be given as 0.4 into 1 minus 0.4, which is 0.6. So 0.4 into 0.6 is 0.24. And S infinity square is P into 1 minus P divided by capital N. So since capital N is infinity, your S infinity square goes to 0. Now you will substitute this in the mixing index formula that we saw in the previous slide. So M is equal to S naught square minus S square divided by S naught square minus S infinity square. So you have the values of each of these variances. 0.24 minus 0.09, which is given in the question. 0.24 minus 0, since your number of particles are infinite. So if you calculate this, your mixing index is 0.625. So here at time t equal to 4 minutes, your M is equal to 0.625. But you need to figure out what is the time taken to have your S as 0.0, S square as 0.05. So in that case, we have to calculate, you have to bring in the concept of mixing time. So as we discussed in one of the previous slides, dm by dt, that is the time rate of mixing, is directly proportional to the amount of mixing that is still left, that is 1 minus m. So your rate of mixing is directly proportional to the amount of mixing that is still left to be done. Dm by dt is directly proportional to 1 minus m. So if you remove the proportionality sign, you will have dm by dt is equal to k into 1 minus m. So if you integrate these from 0 to m and 0 to t, you have ln of 1 minus m is equal to minus kt. So you have m here, you know what is the time. We can calculate k from this equation. So ln of 1 minus 0.625, which is your mixing index, equal to minus k into t, 4 minutes into 60 to convert it into seconds. So 4 into 60 will give you k. So k is 4.0868 into 10 power minus 3. So k remains constant for a particular mixing process. Let's say you're mixing starch and vegetable powder. So for this particular condition, at this particular ratio and all, k K will remain constant for a particular mixing process irrespective of whatever time you are looking at. So K will remain constant. Now you have K, you can calculate M for variance of 0.05. From there you can calculate time T. So to reach a variance of 0.05, you can substitute S square as 0.05. 0.24 minus 0.05 divided by 0.24 minus 0. So your S0 and S infinity will remain the same irrespective of whatever time you are looking at, because at time t equal to 0, you will always have your variance as 0.24, and at time t equal to infinity, since you have infinite number of particles, it will always be 0. So S0 and S infinity square for a particular mixing process will remain constant, and so will K. Only thing that will be changing is S square with time. So 0.24 minus 0.05 divided by 0.24 minus 0. This will give you the mixing index of 0.792. So if you substitute this back inside the equation of mixing time, ln of 1 minus m is equal to minus kt. So ln of 1 minus 0.792 is equal to 4.0868 into 10 power minus 3, which is the k that we calculated from the previous step, into t, which is the time. So if you calculate from there, your time comes out to be 384 seconds. So the answer to this question is option C. So as you can see here, from 4 minutes and your time, you can actually see that at 240 seconds, and when you compare 384 seconds, your M is actually increasing. So your M increases with time. Moving on to question 9. Agitator with a flat blade having a diameter of 0.45 meters operating at 125 rpm is used to mix liquid sample of density 1028 kg per meter cube and viscosity of 0.03 pascal second. The power number obtained for the agitator is 5. Calculate the power requirement for mixing. So we discussed in the previous slides what a power number is. So power number will relate your power requirement for mixing to the operating variables that you have. So you have the operating variables. The diameter of the impeller you have as 0.45 meter. The speed at which you're rotating is given as 125 rpm. The density and the viscosity of the fluid is given, and you also have the power number given. So from there, using the power number equation, you can calculate the power requirement for mixing. So NP is equal to P by rho Ni cube di power 5, where P is the power consumption of mixing, rho is the density of the fluid that you're dealing with, Ni is the impeller speed in RPS, not RPM, Di is the diameter of the impeller, and Np is the power number. So we can substitute these values directly. It's a very straightforward question. Np will substitute as 5. P is what we need to find out. Rho is given as 1028 kg per meter cube. And we have your Ni, that is the speed of your impeller, in RPM. So to convert RPM to RPS, we divide it by 60, which is 125 into 60. Divided by 60 per cube into 0.45 power 5. So from this, you can calculate your power to be 858 watts. So NP is a dimensionless number, and P you will get it in watts. So the answer to this question is option A. So given the kind of the fluid properties and the impeller dimensions and the speed at which it is rotating, you can actually find out how much power it is required to enable the mixing of that particular liquid. So the answer to this question is option A. Question 10. A non-Newtonian fluid is agitated in a tank of 0.8 meter diameter with a 6-plate turbine of 0.4 meter diameter rotating at 180 rpm. Calculate the power requirement for the agitator using the empirical equation NP is equal to 0.4486 Reynolds number per 0.4587. Given the fluid properties, K is equal to 13, N is equal to 0.58, density as 968 kg per meter cube, the average shear rate as 10 into N. It's not 10 newtons, it's 10 into N, where N is the number of revolutions per second of the agitator. So here, as you can see, as we discussed before, your power number can be a function of your Reynolds number. So this empirical equation actually states that your power number is a function of Reynolds number. So first we need to calculate the Reynolds number. From there we'll get the power number, and from the power number you can calculate the power requirement. So what is given here is diameter of the tank is given as 0.8 meter diameter, 0.8 meter. Diameter of the impeller is given as 0.4 meter. You have your your speed of your impeller, that is 180 rpm. So if you convert it into RPS, 180 divided by 60, that will give you 3 RPS. And K, that is your, since it's non-Newtonian fluid, now you won't have a direct proportionality of your viscosity. You will have what is known as an apparent viscosity. This is a concept that was discussed, I think, in week 1 or week 2 itself, when you're dealing with the rheology of the fluids. So since we are dealing with non-Newtonian fluids, we have the consistency index and all. So K is equal to 13 and N is equal to 0.58. Rho is equal to 968 kg per meter cube, and your shear rate is 10 into N, where N is the number of revolutions per second, that is your 3 RPS. So from this, we can calculate your shear rate, average shear rate, as 10 into N, which is 10 into 3, that is your 3 RPS. This gives you 30 second inverse. So irrespective of what you're dealing, okay, so irrespective of the kind of fluid you're dealing with, you can always assume that your shear rate is directly proportional, your shear stress is directly proportional to your shear rate. So if you calculate for a non-Newtonian fluid, it was this is a concept that was given in week 1 as 1 also. So you can refer back as to how the apparent viscosity is equal to K into gamma dot N minus 1, where K and N are properties of the fluid and gamma dot is the shear rate. So shear rate we have already calculated, K and N is already given. So this will give you the apparent viscosity of a non-Newtonian fluid. For a Newtonian fluid, your N will be equal to 1. So in that case, viscosity will not depend upon the shear rate. In fact, viscosity will remain constant. So that is the definition of a Newtonian fluid. Whereas in case of a non-Newtonian fluid, your viscosity will depend upon your shear rate, and hence the apparent viscosity is given as K gamma dot N minus 1. So with the values that is given in the question, you can calculate the apparent viscosity. So mu is equal to 13, which is your K, into 30, which is what we calculated as your shear rate, 10 into N, 30 into N minus 1, 0.58 minus 1. So this will give you 3.116 Pascal second. So this is your viscosity. From viscosity, we can calculate the Reynolds number. So Reynolds number, when you're dealing with an impeller, so this is unlike a fluid flow. Here, when you're dealing with a mixing process, your Reynolds number is given as rho Ni di square by nu. Only when you're dealing with the flow of a liquid, it is rho V d by mu. When you're dealing with an impeller or a mixing kind of a process, Reynolds number or impeller Reynolds number is equal to rho into Ni di square by nu, where rho is the density of the fluid, Ni is the speed at which you're rotating the mixer, the agitator, di is the diameter of the agitator, and mu is the viscosity of the fluid. So we already have all these parameters given in the question, and we have calculated mu as well. So rho is 968 kg per meter cube, Ni is 3 RPS, di is given as 0.4 meters, so 0.4 square, and mu is given as 3.116 Pascal second. So from this, you can find out the Reynolds number in a mixing process, which is 149.11. So this is your Reynolds number. And what is given, an empirical equation is given in the question that relates your power number with your Reynolds number. This is given in the question. So NP is equal to 0.4486, Reynolds number raised to 0.4587. So now you have the Reynolds number, you have you can calculate the power number. So if you substitute the values now, NP is equal to 0.4486 into 149.11, which is your Reynolds number that you calculated, raised to 0.4587. So this will give you a power number of 4.454. So power number is a dimensionless number, hence you will not have any units here. So from power number, you can always relate it back to your power requirement and your operating variables. So NP is equal to P, which is your power requirement, divided by rho Ni cube di phi. Rho is density, Ni is the speed of the impeller, di is the diameter of the impeller. So 4.454 equal to P divided by 968 kg per meter cube, 3 RPS power 3 Ni cube, and di raised to 5 is 0.4 meters raised to 5. So this will give you a power of 1192 watts. So this is how you will calculate the power requirement if you have only the properties of the fluids given and you know the empirical equation between your NP and your Reynolds number. If an empirical equation is not given, you need to calculate the Reynolds number and your Froude's number, and with the Froude's number and the Reynolds number, you have different charts that are present in different books that we are referring to in this certification course. All of those books will have a certain chart for each kind of a turbine. So your power number will highly depend upon what kind of a impeller that you're using, whether how many blades it has, what kind of impeller. So your power number will actually depend upon all these factors as well. So for each of these kind of impellers, you will have different charts, different charts that relates your Reynolds number, your Froude's number, and your power number. So from these charts, you can calculate what is the power number, and from that power number, you can calculate your power requirement. In case you don't have an empirical equation, you need to refer back to a chart that will give a relation between your Reynolds number and your power number. So the answer to this question is option B. So that is all for this week's syllabus. There was a discussion, there was a question posted in the discussion forum related to the humidity chapter that we dealt with. So we'll just briefly discuss about the answer to that particular question. So air at 1 atmospheric pressure, that is 101.325 kilopascals and 30 degrees Celsius with an absolute humidity of 0.0218 kg per kg of dry air is flowing in a drying chamber. The saturated vapor pressure of water in kilopascals is related to the temperature as given below. That is ln Pw naught is equal to 18.6556 minus 5217.635 divided by T plus 273, where T is in degree Celsius. So when you're using this particular equation, T has to be in degree Celsius and not in Kelvin. So if you substitute the T in degree Celsius, you will get your saturated vapor pressure at that particular temperature. So we need to calculate what the relative humidity of air is in percentage. And 4 options are given: 62.82, 68.22, 86.62 and 81.80. So we'll figure out how to calculate the relative humidity of an air. So we'll look at the given. The total pressure of your system is 1 atmospheric pressure, that is 101.325 kilopascals. Your H is the absolute humidity is 0.0218 kg per kg of dry air. Temperature is 30 degrees Celsius. So what is relative humidity first? Relative humidity is the amount of water vapor that is present in the air to the total amount of water vapor that can exist at that particular temperature. So this amount of water vapor in the air can be given as your vapor pressure PV, and the total amount of water vapor that can possibly exist in that particular temperature can be given by saturated vapor pressure. So generally in our lectures, we have been dealing as your saturated vapor pressure by the notation PS. So we've been using PS as your saturated vapor pressure. But in this particular question, saturated vapor pressure has been given as P0W. So we need not get confused with PS and P0W, which is same in this question. So we'll first calculate how to find out relative humidity. So relative humidity, the total amount of water present, which is given by your vapor pressure, divided by PS, which is the total amount of water that can possibly exist in that particular temperature, given by your saturation pressure. So PS is nothing but P0W in this question. So we'll calculate PV and PS first. So vapor pressure, when you have absolute humidity given in a question, you can calculate the vapor pressure by this particular equation that was discussed in one of the lecture videos as well. So H is equal to 0.62 PV minus P minus PV, where PV is your vapor pressure, P is your total pressure of your system, and H is your absolute humidity. So you have absolute humidity given in the question, you have the total pressure P given in the question, you need to calculate PV and substitute back into the relative humidity equation. So if you substitute the values, H is equal to 0.0218 kg per kg of dry air, 0.622 PV by 101.325 minus PV. Both these PVs are the same, although it looks different because of the font. Both these PVs are same, that is your vapor pressure. So from this you can calculate your vapor pressure. If you transpose the denominator to this side, you have 2.208 minus 0.0218 PV is equal to 0.622 PV. So you can calculate PV as 3.431 kilopascals. So since you're substituting P also in kilopascals, you will get PV also in kilopascals. So PV is 3.431 kilopascals. So now we have your vapor pressure. We need to find out what is the saturation vapor pressure. So the equation for that is given in the question. Ln Pw naught, which is the same as Pw naught is same as PS that we are dealing with in our lecture videos. Ln of Pw naught is equal to 18.6556 minus 5217.635 divided by T plus 273, where T is substituted in degrees Celsius. So if you substitute the value of T, which is 30 degrees Celsius, you get your PS, which is equal to P naught W, as 4.2025 kilopascals. So if you if you calculate the value and take an exponent of this value, you get 4.2025 kilopascals. And it is already mentioned in the question that whatever saturation pressure you get here is in kilopascals. So now all you have to do is substitute PV and PS into this equation to find out your relative humidity. So relative humidity is asked in percentage. So you divide PV by PS. So you multiply PV by PS into 100. So PV is 3.431 kilopascals. PS is 4.2025 kilopascals into 100. So your RH comes out to be 81.64%, which is close to your option D. So the answer to this question is option D. So I hope the doubt posted in the discussion forum is clear. If you guys have any doubts in any of the lecture videos or the problem solving sessions, you can again post it in the discussion forum and we'll take it up in the next problem solving session. Thank you.